Okay. Now they did something to me that's weird. That, this is kind of a strange thing. You can still do that. What else can I do? Let's see. Cool. That's interesting. So you can do a thickness. They'll still let you do that. Okay. Well, that's good. That's good enough for me. They won't let you do that anymore. They'll let you have one pin. I don't need more than one pin anyway. So I wonder if I could get those off of there. Then there's they'll probably eventually take that away too. Yeah, there's a feature that, I wonder if that's part of their funny feature. That's funny. Okay. Oh, so I guess I've got to go online to do this one because I don't have. That does. I don't know what that's doing. So, do y'all have any questions about any of the problems? I think I'm staying ahead of the problems with the lecture. I think. If I'm not, let me know. I think what I'm gonna do is just dig in there, and as soon as I get in, I can start going to. Hey, what's this? This is a new thing. Let me let it come up and see what this new. That's something new. Channels. Watch our videos. Okay. Let me let it come up. Okay. Let's see. Whoa, that's interesting. Okay, what? Open channel. Dive into the Tesla's content and open channels. What the heck is that? Get exam ready with videos to practice problems. Sure. Start playing for free. Okay. Explore the catalog. Math, physics, social science. You think it's maybe under physics? They may not have engineering. Yeah, well, doesn't look like they've got that, but they've got some new button there. Now I don't know how to get rid of it. Oh, here we go. Okay, so he's done this section on conservation of mass. Then he does energy, and then he does momentum. Usually most books do mass, then momentum, and then energy, but I'll just follow what he's got. So what I'm going to do, let's see how he does this first. And okay, so he starts here. He runs in, and he just pops out the answer. Okay, so that's interesting. So that's Bernoulli's equation. So let me put it in an interesting context. Usually in the other book, they spend more effort deriving that up, but it's something that's actually a lot simpler than it seems like. So if you look at the equation, a lot of people like to list it like this. And then they took the rho and the g and the z, and it equals to another constant. It's still equal to a constant, but you're just multiplying everything times rho to get this one. So this is a different constant. So if you think about this, I'm going to relate it to something else. I'm just going to hold on to that mindset. And I'm going to relate it to something else. So back in dynamics, or in physics, you had mv squared, 1/2 mv squared, plus mgh. So if you had a ball, for example, and you just dropped it, you would set up a datum. Okay, so let's say you set your datum up right here. You call this, okay, I'll call it Z or H, depending on which one you'd like. And then you have a ball that's a mass M, and then it goes down to here. And say you released it from rest, and say you picked up the energy. So say it was released from rest. So what you would do, 1/2 mv squared plus mgh equals to 1/2 mv squared plus mgh. Now, what you were doing is you were saying, here's a spot right here, and then a few seconds later, here's the same spot, but the ball, the marble, went from spot 1 to spot 2. So in essence, it was a constant. And so then you said 1, 1, 2, 2, and then you started working out the problem, and then you found out 1/2 mv squared is equal to mgh. Then you could cancel out your masses and do stuff like that. So what you were doing is you were tracking your marble. You were sitting on your marble and you were watching it flow downhill somehow. Now, let's think about this and compare. Now you can immediately see there's something very similar here. And what the similarity is based on the volume. So let's say over here you had a water balloon. There you go. So this is a water balloon. So it has a particular volume, and it goes down to here. Now the volume might change, but usually might not. And then if you start looking at these, you start saying, well, the mass per unit volume is this, rho v squared, and then the mass per unit volume there, that's supposed to be a plus rho gh. But up here it's written as a z, down here it's written as an h. So that's why I said it's either h or z right there. So already you're starting to see, hey, wait a minute, this is just the old standard equation, except I've got this. And so how does this play into this? And, back in dynamics, you had something like an F dotted with an X, So if you had say you had a block on a plane and it didn't have any friction and you shoved it, it moved it over to here. You shoved it with an F, and then say it went a certain X, and they're both going in the same direction, then essentially this is the added amount. So if this had an initial velocity equals 0, by here, velocity is not equal to 0. It's going to be something greater than 0 because you pushed it and it's moving along. Now, if you want to look at the implications of the dot product, shove it like this, and you'll realize this is the component going in the direction of X. This component is a wasted amount of force. So that's the dot product part. But let's just assume that for the moment that we're just pushing the block that way. Now let's imagine this. Let's imagine this block is a disc. And this disc is being pushed on the backside by a higher pressure, and this disc moves. So here, this disc itself moves to the right some amount of delta x. Now, here, the area of this, so it's in a pipe, say. Doesn't have to be, but this makes it seem a little bit more normal. So what is the force? It's the pressure, pounds per square inch. You know, pressure is force divided by area. So it's pounds per inches squared, or it could be feet squared. So pressure that's being pushed on there is the force divided by the area. Well, now we're saying we're taking this force and we're shoving it some distance delta x. Say it moves it to the right, say some delta x. Well, the question is, how do I get volume out of here? So what is pressure equals something here, F dotted with X over volume. Okay, I should have written this down here. Let's see if I can move it. I may have to move it incrementally. Okay, hang on. Okay. So, okay, my brain is freezing a little bit. So my pressure is that. Is that equal to F times, wait a minute. Okay, wait a minute. I want to write this a little bit differently. Here's what I want to do. I want to do F delta X is equal to, now I want to take the force out, put the pressure over the area, and then say delta X. But if I did this, and I did that, in other words, okay, wait a minute. What am I missing here? No, wait a minute. Wait. The eventual thing that's supposed to come out of here is this is the same thing as this. The volume. So, in other words, this term and the volume is nothing more than the area of the thing times delta X. So, in fact, this term ends up being that cancels that, and that ends up being pressure. Now, okay, did I get that out of this? Okay, so I've kind of run in circles over here. So, so it is true. I may just stick back with that. So, in other words, this and this are related because I divided by the volume. So in other words, am I making sense, or am I just talking myself into circles here? So it's a F times X times over the volume. So anyway, I'm talking myself into circles here. But now let's use this thing. Um, so here we go. Let's say you want to measure, and actually I'm doing this right now. Let's say you want to measure the flow through this, through a pipe, but you don't want to mess with the flow too much. So maybe you just want to have it a small restriction here. So let's say this area will equal to 1, and this area out here is equal to 10. Well, let's make it 2, so that it's not too much of a restriction. Okay, so what we're going to do is we're going to do something interesting. There's two ways you could do this. What I'm doing right now with mine is, this is not critical to a lecture or anything, but what's it called? EME 280? Yeah, so what I'm doing, here we go. I'm buying 2 of these. Give it a second. And I'm hooking them to a Raspberry Pi. Oh, there's a bunch of them right there. I didn't buy any of these. But what it is a tiny, 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 tiny pressure transducer right in that little square right there. And then you hook these things. Mine didn't come this way, but you hook these things to this. It looks like you got to solder those onto here. And then if you go out and look, you can do, yeah, well, I don't know what I'm doing. Okay. EME 280. You'll find a bunch of people who have this kind of set up already. Obviously, there's people that do videos, but let's see. Oh, that's what? I mistyped it. Okay, so here's a person that his looks like that. I should go back and look at mine again. Maybe mine does look like it. You connect these things up, put them to a Raspberry Pi, and then you can get this script and basically plot your pressure through time. So that's not that critical for the lecture, but essentially what I'm doing is I'm trying to find the airflow through this thing. And so I'll put one of the sensors here and one of the sensors here. And I basically, eventually I'm going to have 2 of them plotting each other. So we'll do that for the moment. Let's just say we have P1 and P2. We have them as a function of time because mine's going to be set unsteady. So I'm basically having flow rate, lower flow rate, faster flow rate. I should be getting flow rate that kind of is at a basic level and then goes fast, slow, and fast and slow. So that's what I'm looking for. So if I can track this and see over time, what's the mass flow through there? But how do I do that? Well, I'm going to assume it's water right now. And so we got spot 1 and we got spot 2. And so we write down the equations, P1 plus rho. Now, mine's air, but mine's not flowing fast enough that the density is going to be any different. So rho velocity 1 squared over 2 plus, he has rho g and z, but most textbooks combine these together to give you gamma, is equal to pressure 2 plus rho V2 squared over 2 plus gamma Z2. So it's like the marble. You're very interested in the fact that you're going to stare at 1 and stare at 2. And, in my case, I'm 3D printing this little valve. So I've got to put these points together really close. But what you find out is you're using, it's just like writing the energy equation. F dot X plus 1/2 mv squared plus mgh is equal to the stuff on the right hand side. Now I'm just basically, it's equal to a constant. So let's say I get P out of here, and the first thing I realize about this is that I have continuity that occurs between as the particles flow down through here. So I can get, before I go, I can get V1 as a function of V2. And the way I get it is like this. And I didn't want to put diameters, I just wanted to put the two areas. So area 1 is 1. Sorry, area 2. Okay, I'll assume, and this is in my case, the pipe, I'm doing a fitting in there. So my pipe is a little bitty, and then it has to be the same because the connectors are the same. I have to pull them apart, put this connector, and put them back together. So, in fact, this is 2. V1 is equal to 1 V2. So, V2 is equal to twice what V1 is. So, whatever this is twice the length of it. So I speed up. And since I speed up, the pressure at 2 is going to drop off. So what I'll do is I'm going to take this and put it right up in here. I'm also going to recognize that the elevation is the same. And so this and this can be canceled out. And so as a result of this coupled with this one, I get P1 plus rho. Now, you get V1 squared over 2 is equal to P2 plus rho. Now I'm sticking this in for V2. So I'm going to square that term, and I'm going to square this term. So I'm going to get 4 V1 squared over 2. And I don't have anything else. So, depends on the way you want to do this. I could move this over here and this over here and say P1 minus P2 is equal to, you take 4 and you take off 1, so you get 3 rho V1 squared over 2. Now, if you know your material, let's just say it's water. And you put this in and you get 3 times 1.94 over 2 times V1 squared. P1 minus P2. Now, your key is can you figure this one out? If you take your Raspberry Pi and you get these numbers out as a function of time, then you can actually take the V1, here it'll be V1 is equal to square root of, and you know what? I'm going to write it back in this form because mine's going to be air, so I'll get 2 times, you know what? I'll go ahead and say P1 minus P2. I was going to say delta P, but about 3 times the density. Now, if I do this, I basically, for me, I could get this as a function of time just by going in. And if I had a strip chart of like P1 and P2, so say I had P1 and then say P2, and it's this and that, it's easy to put these in variables and subtract them, multiply it times 2, divide by 3, and then go ahead and put in the density of air. So you can basically get that. And so you don't have to interfere with the flow that much in order to get the flow rate out of it. One of the things you could find out is the area ratio. So if you think about it, this 2 came in area ratio. If your area ratio becomes 1, then you got a problem. So in other words, if you just stuck a piece of pipe and you did this, the areas are the same. And let's think about that. Okay, so your area ratio being 2 got stuck in here as this 4. So let's go in a general sense. You know, P1 minus P2 is equal to, okay, the 4 is the area ratio squared. So it would be area ratio. Maybe I should do ratio of the area. How about that? Ratio of the areas squared. And it should be V1 squared over 2 with the density in front of it times rho V1 squared over 2. So what you end up with is P1 minus P2 equals to rho V1 squared over 2, the ratio of the area squared minus 1. So if the ratio of the area squared is equal to 1, then you're not going to get any difference in the pressure. You can't figure out the velocity from that. So then the question is P1 minus P2. Okay, so if I turn around and take this, well, here we go. And I say V1 squared is equal to square root of 2 V1 minus P2 divided by rho ratio of the area squared minus 1. So again, if you put in 1 there, this is not going to be good because you're going to show the V1 is infinite. But the situation such that you're going to find the pressures are going to be equal, or you should. And if that's the case, then you're stuck because you just have a 0 over 0. The key is really this. If you had the ratio of the area equal to, say, what I had initially, what did I have? I had the ratio of the area being 2. Let's say you end at 1.001, then the V1 will be very sensitive to the pressure, so you might get a lot of error in that. So you got to be careful that you have enough change in area, but not too much. The last thing you want to do is do like this, and then you've restricted your flow. So you're looking at the pressure difference between those two. So you've restricted your flow so much, you've slowed it down. And so then the thing is, if you had your area too big, you know, where it did that, just a very tiny amount, when you put your taps there, you're going to end up with not a very accurate picture of your flow rate. So it just depends on your circumstances. But the key is we just use this to write between those two. There's another way of picking up flow rate, and it's with something called a pitot tube. And I wonder if he has that in there somewhere. I don't know. Let's just go down through here and see if he has a pitot tube down here. It may be too early for us to have that. Well, here, I'll just, since I don't know where it is, all airplanes have this, and you can go out and look at them. There you can buy a bunch, but it's a pretty simple. Okay, I think I clicked it. Okay. Okay, so there's a. So what happens? Okay, so I'll go ahead and use that picture, but what you find out is most pitot tubes are the last one. Here's what I mean. So if you have this one, okay, so what happens with these is you're supposed to put them in the middle of the flow stream. So here's your flow coming at you. And what happens is on this one, on the top one, you pick your point being right here, say 2, and then your point being back here, say 1. And this point back here has a velocity, say just v. But what happens up here is the velocity here, interesting. Okay. The velocity up here is equal to 0. Why? Because actually back in here, somebody put some type of pressure meter, like right here. What I'm going to do is I have a little plastic encasement, put the wires through there, and I'm going to silicone it, and just put the little thing in here, and in that container, as long as it's somewhat rigid, the flow is going to be 0 in there, so it's just going to register the pressure fluctuation. But there's not a hole. If there was a hole in here, the flow would have come up through here. But the fact that there's no hole, hopefully, then that means all throughout this tube, the velocity is equal to 0, which means at the very tip of that tube, velocity is equal to 0. So if you write Bernoulli's equations between those, you get, here, what's going on? You get P1 plus rho V1 squared over 2. And assuming that these are at the same datum, you don't even have to write the other one. P2 plus rho V2 squared over 2, but that velocity is 0. So just right there, you get P1, P2 minus P1 is equal to rho V1 squared over 2. But you have the ability to measure this pressure. What's the pressure out here? Can you get that? And that's where you've got this one. So what you have here is you write between here and say this point, and if the velocity is the same, this will pick up the static pressure, this pressure on the side. So you can write between here and here. That doesn't really matter. What you're going to get is the pressure here is the same as the pressure here. And if this pressure becomes lower, it'll suck stuff out of here. If it becomes higher, it'll push back in there. But if the flow just goes like so, from left to right, and there's nobody goofed up like constructed it with something like this on the edge. I think that color. Let's say, where was that? Let's say somebody made it and they left a burr on here. And what will happen is the flow will have to come up and turn, and it'll have to come back down. So in the turn back down, it'll produce a lower pressure here. If in fact it was the reverse, and say they left a burr on here, then what's going to happen is the flow is going to come up. It's going to have to turn. If it's turning, something's going to have to push it up, meaning that this is going to be a higher pressure. But if you had flow coming straight over this, this is picking up the static pressure, or the pressure that exists in these two equations. So there's your static pressures right there. Meaning you need a combination of these. You need a pitot tube that does this, and you need a pitot tube that does that. Well, in came this one. So what you do here is you write Bernoulli's equations between 2 points that are so close together that their energy is the same, and one stagnates right there, and then the other just goes up and over right here. So here you're picking up the static, and here you're picking up what they call the dynamic pressure, which is essentially P of the static pressure plus the energy. So you have an energy that's associated with this plus a rho v squared over 2 because it got stagnated. Okay, so let's call this 1 S. So in other words, you take all that kinetic energy, you kill it off here, and because of that, you get an increase of pressure. And it increases, this is the static, and this is the increase back here. And so this is the stagnation. It's a stagnation point. So I had a case years ago where I had to work on a thing where wind loads were important. And they were wanting to know what's the worst case scenario for like a 60-mile-an-hour wind. Might have been 100, I don't remember. But it was a little tower. And so I just took the platform area. Okay, so you're just trying to do a quick calculation. And if it's a three-dimensional situation, there's going to be a point that'll come in and stagnate on here, and the other points are going to come in and turn and go off the object, you know, in all directions. So you're going to have a really high pressure there, but then you're going to have a decreasing pressure around there. So what I did is I said, well, what happens if you have the entire face is stagnating? That's not going to happen, but that's the worst case scenario. So what you do is you just say, what's the area here? And what's the stagnation pressure? And that's pounds per square inch, and then the area inches squared, and or feet squared. And so you just multiply that, the pressure stagnation times the area. That gets you a very conservative look at what the worst case scenario is. What's the stagnation? That's just the atmospheric plus rho air v squared over 2. And so you just put in there 100 miles an hour, take the density, you know, square that, add the atmospheric, multiply times the area, and that gets you the worst case scenario of the air pressure on that surface. That doesn't include any dynamic loads because there could be shaking that's going on. But this was a structure that was very, very stiff, had low mass to it. Frequency of vibration was really high. First mode was. And so what happened is I did that, calculated. I probably, with that, you probably have factor of safety of 5 or 6. And it was well designed. It could have taken 200-300 mile an hour winds. But they just wanted for 100 mile an hour for some reason. So stagnation occurs at a point, but you could, as an engineer, you can just use that as the worst case scenario and figure out the worst case load to figure out if you pass, you know, if something's going to happen. So you think about it. Let's say you put, I'm not sure I can do a decent job. Let's say you had a pipe that went here. So this is connected here. It goes down here. And then there's this little pipe that comes off here. And then what happens is you put water in here, or mercury, or whatever. Since this is stagnation, this one's going to be a higher pressure than this one. Then any sort of water you have is going to be moved back and forth like this. And so you're going to get a height right here. And here's your water. Say the rest is air. Or it doesn't have to be air. It's just that this needs to be heavier than the lighter. It doesn't work well if you don't have that, because it'll just flush the manometer fluid right out. In other words, if this was put in mercury and then you had water right there, you turn the thing on, the first thing that's going to happen is just going to flush this out through here, and it's going to come out the sides here, and it's going to be gone. And then you don't have a manometer at all anymore. So how do you calculate this? And this is a fairly common thing. In other words, we have this in the fluid lab. And this is how you calculate the flow. And it's incredibly accurate and incredibly inexpensive. You just have to buy a pitot tube, which I don't know what they would cost, but I was right there. Let's see. There's a pitot tube for $19. I don't know how big it is. Oh, well, it tells me how big it is. It's stainless steel stay tube, 5 by 2. I don't know which is measured, how this is measured, So there's your, does he put the dimensions down? I'm assuming 5 is this distance this way, and the 2 is the distance that way. But you notice what he's got. There's 2 holes drilled on the side. That's a really ugly looking drawing. That's really not very. That's really not very good. Let me get in there closer. Okay, this is just a static tube. So this doesn't have both. Let me show you why. Why would you want a static tube, one without the other? I can show you that real quick, and then we'll work some problems. Say you take that static tube and you run out to, there's a stream running past you and it's running really fast. And then you stick that static tube, or actually, no, it's a static tube. It's not, let's assume you just, okay, stuck a straw in the water. Then without the dynamic tube, you pretty much, you got to have the other tube. So otherwise, it's just a waste of money. It's only $19. So let's say you stuck that in the water. Then because this stagnated, the water would come up here. And that distance right there is going to give you the flow rate. So we'll calculate that next time. And we'll do some other ones. So let me see if he's got, okay. I do not know where the problems are associated with this, but maybe they are at the end of that. Applications of the moves, then a bunch of problems. Energy and hydraulic grade line. The energy equation, we'll save that for thermo. Because most of the time, here, let's look at it. Most of the time, you'll start talking about, well, okay, head of the pump. Maybe I will cover that because he's just talking about pump and the, okay, so I will do that section. Okay. Okay. Wait, that's, okay. This thing is, where am I at? I'm still on that. I wanted to push there. Is it just that I wasn't patient enough? Okay. Wait for the circle. Okay, here we go. So we'll just go through and do a bunch of these problems next time. And I'll just do them fairly rapidly because okay, that's cheating. So he tells you the pressure at A. He wants to know the pressure there. So that's pretty straightforward. We'll just do a pile of them. Just rapid fire a bunch of them out of here. Do a bunch here. Then we'll go into the problems themselves. And he is including head loss and head gain through. Let's see. Does he have anything? Is there any pumps in here? Well, we'll just go through a bunch of them. What is that? The sewage siphon regulates the level in large holding tank A. Determine the flow rate through a 3-inch level. So, oh, okay. So it's just you have to assume that there's no air bubbles in there. That's a pretty simple problem, but oh, and this is interesting too. So a way of producing energy, you can see people do this, is a tapered channel which diverts seawater into reservoir. So the wave comes in. As the wave approaches the shore, it's closed through the closed tapered channel at A. The height will begin to increase until it spills over into the side of the reservoir. The water in the reservoir pass through a turbine to build in C to generate power. And actually, I've seen a couple of these. The speed of the water is that, the water depth is this. Determine the minimum height in the back of the channel to prevent the water from entering. Determine the minimum height H at the back of B of the channel to prevent water from entering the reservoir. So that's actually a pretty simple calculation, but I don't know if that's a true acronym or not. Just out of curiosity. Okay, I actually thought I copied that. Did they not? Okay, wait a minute. Oh, okay. I knew you can copy that. Okay. Let's just see if that's a true acronym. Oh, it is. Okay. That looks like the same picture right there. That's not it. That's a table. That's that too. So there's two. Okay, some sort of interesting. There you go. Weebly. I don't know what a Weebly is. And that's it. There's not much there. How does it work? So see, y'all could build one of those, except you have to get close to the ocean. Otherwise, it's kind of not very pointful. Doesn't make any use. But I guess, I may just call it quits and then we'll just rapid fire out a bunch of problems next time. And maybe what I'll do is maybe we'll virtual Friday and then I'll just rapid a bunch of problems out that way too. That way they'll all be there. Man, when I sit here, my brain goes dead. I can't imagine sitting out there. and then your neck tightens up. I need to go lift weights. I need to go to the gym, but I have advising I got to go do.